I've done a bunch of videos where I use words like pressure and, let me write these down, pressure and temperature, and volume. And I've done them in the chemistry and the physics playlist. And then especially in the physics playlist, but even in the chemistry playlist, I also use words like kinetic energy, kinetic, I'll just write E for energy, or I use force, and velocity. And a whole bunch of other types of, I guess, properties of things, for better or for worse. And in this video, what I want to do is I want to make a distinction, because it becomes important when we start getting a little bit more precise, especially when we get more precise in thermodynamics, or I guess the study of how heat moves around. So these properties right here, these are properties of a system, or we could call them these are macrostates of a system. Macrostates. Macrostates. And these could be macrostates. So for example, let me make it clear. When I call a system, if I have a balloon, if I have some balloon like this, and it has a little tie there, and maybe it has a string. This has these macrostates associated with it. There is some pressure in that balloon. Remember, that's force per area. There is some temperature for that balloon, temperature. And there's some volume to the balloon, obviously. But all of these help us relate what's going on that inside that balloon, or what that balloon is doing in kind of an everyday reality. Before people even knew about what an atom was, or maybe they thought that there might be such an atom, but they'd never proved it, they were dealing with these macrostates. They could measure pressure, they could measure temperature, they could measure volume. Now, we know that pressure is due to things like you have a bunch of atoms bumping around, and let's say this is a gas. Well, if it's a balloon, it's going to be a gas. And we know that the pressure is actually caused, and I've done several. I think I did the same video in both the chemistry and the physics playlist. I did them a year apart, so you can see if my thinking has evolved at all. But we know that the pressure is really due by just the bumps of these particles as they bump into the walls of the side of the balloon. And we have so many particles that at any given point of time, some of them are bumping into the wall of the balloon. And that's what's essentially keeping the balloon pushed outward, giving it its pressure and its volume. We've talked about temperature as essentially the average kinetic energy of these balloons, which is a function of these particles, which could be either the molecules of gas, or if it's an ideal gas, it could be just the atoms of the gas. Maybe it's atoms of helium or neon or something like that. And all of these things, these describe the microstates. So for example, I could describe what's going on with the balloon. I could say, hey, I could just make up some numbers. I could, the pressure is let's say it's 5 newtons per meter squared, or some number of pascals. The units aren't what important. In this video, I really just want to make the differentiation between these two ways of describing what's going on. I could say the temperature. I could say the temperature is 300 Kelvin. I could say that the volume is, I don't know, maybe it's 1 liter. And I've described the system, but I've described it on a macro level. Now, I could get a lot more precise, especially now that we know that things like atoms and molecules exist. What I could do is I could essentially label every one of these molecules, or let's say atoms, in the gas, or that's contained in the balloon. And I could say at exactly this moment in time, I could say at time equals 0, molecule, atom 1 has, its momentum is equal to x, and its position in 3-dimensional coordinates are x, y, and z, right? And then I could say atom number 2, its momentum, I'm just using rho for momentum, or p, it's equal to y, and its position is A, B, C. And I could go and give you this. I could list every atom in this molecule. Obviously, we're dealing with a huge number of atoms, on the order of 10 to the 20 something. So it's a massive list I would have to give you. But I could literally give you the state of every atom in this balloon. And if I did that, I would be giving you the microstates, or I would give you a specific microstate of the balloon at this time. Now, when a system, and I'm going to introduce a word here because this word is important, especially as we go, is in thermodynamic equilibrium. So let me write that down. Equilibrium. Equilibrium. And we learned about equilibrium from the chemistry point of view, and that tells you, the amount of something going in the forward reaction is equivalent to the amount going in the reverse reaction. And when we talk about macrostates, thermodynamic equilibrium essentially says that the macrostate is defined, that they're not changing. If this balloon is in equilibrium, at time 1, its pressure, temperature, and volume will be these things. And if we look at it a second later, its pressure, temperature, and volume will also be these things. It's in equilibrium. None of the macrostates have changed. And actually, I'll talk about in a second, in order for these macrostates to even be defined, to be well defined, you have to be in equilibrium. I'll talk about that in a second. Now, at time equals 0, you might have this whole set of, I went and I listed 10 to the 20th something microstates of all of the different atoms in this molecule. But then if I look at these gases a second later, I'm going to have a completely different microstate, right? Because all of these guys are going to have bumped into each other and given each other their momentum, and all sorts of crazy things could have happened in a second here. So I would have a completely different microstate. So even though we're at thermodynamic equilibrium and our macrostates stayed the same, our microstates are changing every gazillionth of a second. They're constantly changing. And that's why, for the most part, in thermodynamics, we tend to deal with these macrostates. And actually, most of thermodynamics, or at least most of what you'll learn in a first-year chemistry or physics course, it was devised or it was thought about well before people even had a sense of what was going on at the macro level. And that's often a very important thing to think about. Sometimes and we'll go into concepts like entropy and internal energy and things like that, and you kind of rack your brain, how does it relate to atoms? And it's sometimes, and we will relate them to atoms and molecules, but it's useful to think that the people who first came up with these concepts came up with them not really being sure what was going on at the micro level. They were just measuring everything at the macro level. Now, I want to go back to this idea here of equilibrium. Because in order for these macrostates to be defined, the system has to be in equilibrium. And let me explain what that means. If I were to take let's say I were to take a cylinder, and we will be using this cylinder a lot. So it's good to get used to this cylinder. Get a cylinder there, and it's got a piston in it. And that's just it's kind of the roof of the cylinder can move up and down. This is the roof of the cylinder. The cylinder is bigger, but let's say that this is a kind of a roof of the cylinder, and we can move this up and down. And essentially, we'll just be changing the volume of the cylinder, right? I could have drawn it this way. I could have drawn it like a cylinder. My drawing skills I could have drawn it like this, and then I could have drawn the piston like this. So there's some depth here that I'm not showing. We're just looking at the cylinder front on, right? And so at any point in time, let's say the gas is between the cylinder and the floor of our container. We have a bunch of molecules of gas here, a huge number of molecules. And let's say we have a rock on the cylinder that essentially, let's say we're doing this in space. So everything above the piston is a vacuum. Actually, let me just erase everything above. So let me just erase this stuff, just so you see it. We're doing this in space, and we're doing it in a vacuum. So let me write that down. So all of this stuff up here is a vacuum, which essentially says there's nothing there. There's no pressure from here. There's no particles here. It's just empty space. And in order to keep this, we know already, we've studied it multiple times, that this gas is generating, things are bumping into the wall of this, the floor of this piston all the time. They're bumping into everything. Right? We know that's continuously happening. So we need to apply some pressure to offset the pressure being generated in the gas. Otherwise, the piston would just expand. It would just move up, and the whole gas would expand. So let's just say we stick a big rock. We stick a big rock or a big weight on top. Let me do it in a different color. We put a big weight on top of this piston, where the force is completely offsets the force being applied by the gas. And obviously this is some force over some area, right? The area of the piston over some area, so we could figure out its pressure. And that pressure will completely offset the pressure of the gas. But the pressure of the gas, just as a reminder, is going in every direction. The pressure on this plate is the same as the pressure on that side or on that side or on the bottom of the container that we're dealing with. Now, let's say that we were to just evaporate this. Well, let's not say that we evaporate the rock. Let's say that we just evaporate half of the rock immediately, right? So all of a sudden, our weight that's being pushed down, or the force that's being pushed down, just goes to half immediately. Let me draw that. So I have, maybe I was better off just cut and pasting this right here. So if I copy and paste it. So now I'm going to evaporate half of that rock magically. So let me take my eraser tool, and I just evaporate half of it. And now what's going to happen? Well, this piston is now applying half the force. It can't offset the pressure due to this gas. So this whole thing is going to be pushed upwards. But I did it so fast. You could try it. I mean, this would be true of a lot of things. If you had a weight hanging from a spring and you just remove half the weight, it wouldn't just go very, nice and smoothly to another state. What's going to happen is, and let me see if I can do this using their cut and paste tool. It'll essentially, right when I evaporate half of it, the gas is going to expand a bunch, and then this weight is going to come back down. It's going to spring and go down. So let me do it again. It's going to expand because that gas is going to push up, and then it's going to come back down, and then it's just going to oscillate a little bit, and then eventually it'll come back to some stable, and maybe it'll go back. It'll be like right about there. And let me fill this in. This shouldn't be white. This should be black. Let me put some walls on it, on the container. Some walls on the container. So if we wait long enough, eventually we'll get to another equilibrium state where this thing isn't, the piston on top isn't, or the ceiling isn't moving anymore. And now the gas has filled this container. Now, at this point in time, we were in equilibrium. The pressure throughout the gas was the same. The temperature throughout the gas was the same. The volume was in a stable situation. It wasn't changing from second to second. So because of that, our macrostates were well defined. Macrostates, well defined. Well defined. Now, when we wait long enough, this thing will get to some stability where this thing stops moving. When this thing stops moving, our volume stops changing. And hopefully our pressure will become uniform throughout the container, and our temperature will become uniform. It will now be a higher volume, a lower pressure, probably a lower temperature if we assume that there's no other heat being added to the system. And then we'll be well defined again. Will be well defined again. So we could say what the pressure and the volume and the temperature is going to be. But what about right when I removed this rock and this thing flew up and it oscillated, and for a while the pressure at the top was lower than the pressure down here. Maybe the temperature at the top was lower than the temperature down here. The whole thing was in a state of flux. It was not in equilibrium. And at that point, when let me draw that really. So when we were in that state where everything was just crazy, right when we evaporated the rock. We have a little rock up here. It's going up and down. Maybe the pressure up here was lower than the pressure than the pressure down here. The temperature was lower than the temperature. Everything did not have a chance to reach an equilibrium. At this state, and this is important, especially as we go into talking about things like reversible reactions and reversible processes and quasi-static processes. At this point in the reaction, when we just did this, none of these macrostates were well defined. You couldn't tell me what the volume of the system is because it's changing for every second to second, or microsecond to microsecond. It's fluctuating. You couldn't tell me what the pressure of this system is because it's changing every second. You couldn't tell me what the temperature is. Maybe the temperature could be, if I did this as the temperature could be something there. It could be something there. All sorts of crazy things are happening. So when the system is in a state of flux, your macrostates are not well defined. And I really want to hit that point home. So let me just draw that in a diagram. Let me draw that in a PV diagram. And we're going to use these fairly heavily. So on my y-axis, I'm going to put pressure. In my x-axis, I'm going to put volume. So Our initial state here, when we had the rock sitting on top of this ceiling, this movable ceiling, or this piston, maybe we had some well-defined pressure and volume. So my y, so this is pressure, and this is volume. So this is where we started off. So it was well-defined. This is state 1. Let me label it right there. This is state 1. Now, when we evaporated half the rock, we eventually, and we waited long enough, and this got to an equilibrium, we got to state 2, and our pressure, volume, and our temperature was well defined. And I'll just put it on this pressure, volume. So maybe this is state 2. We got down here. And just as a side, I could maybe put temperature as an extra dimension, but temperature is completely determined by pressure and volume, especially if we're dealing with an ideal gas. Remember, and we did this in multiple videos, you have PV is equal to nRT. These are constants. The number of moles isn't changing. This is the universal gas constant, not changing. So if you know P and V, you know T. So that's the only two things we have to plot. But I'll talk a lot more about that in future videos. But the important thing to realize is I started off at this state where pressure and volume were well defined. I finished in this state where pressure and volume were well defined. But how did I get there? And because this reaction, I did it all of a sudden, it happened super fast, and it was essentially thrown out of equilibrium. Out of equilibrium. I don't know how I got here. The pressure and volume were not well defined from going from that state to this state. Pressure and volume and temperature are only well defined if every intermediate step is still almost in equilibrium. And we'll talk a lot more about that in the next video. But I want to really make this point home. It would be nice if we could draw some path. We could say, we moved from some pressure and volume to some other pressure and volume, and we moved along a well-defined path. But we cannot say that, because when we went from there to there, our definitions just disappeared for pressure and volume. We cannot define those macro states in these intermediate non-equilibrium states. Now, just as a little aside, we could have defined the microstates. The microstates never change. At any given snapshot in time, I could have listed every particle that's in this thing, and I could have given you its kinetic energy, I could have given you its position, I could have given you its momentum, and there's no reason why I couldn't have done that. So I could have actually made I could have made a plot of one particular particle, and I could have said what its kinetic energy and its over at a course of time is at any given moment in time. And this is really important. So microstates are always well defined. The microstates, what's exactly happening to the atom in terms of its force and its velocity and its momentum. While macrostates are only defined, I should say, well defined when the system, in this case it's the balloon, in this case it's this piston on top of this cylinder, this movable ceiling. The macrostates are only well defined when the system is in equilibrium, or where you can essentially say, when you say the pressure is x, the pressure is the same throughout, or the volume isn't changing from moment to moment, or the temperature is the same thing throughout. Anyway, I'll leave you there, and we'll talk more about why I went through all of this pain in the next video.